Hi guys, in this video we'll discuss antidifferentiation and U substitution. Let's go. So we say that the function capital F is an antiderivative of the function small f on an interval capital I if the derivative of capital F of x is equal to small f of x for every value of x in capital I. We see here that it says an antiderivative. This follows from the fact that a function can have several antiderivatives. Next, let's look at some theorems that concern antidifferentiation. So when you want to look for an antiderivative of a function, you will make use of integrals. So in this first theorem, we see that if you get the antiderivative of 0 with respect to x, you'll get the indeterminate constant, any constant, which we denote by a capital C. This follows from the fact that if you get the derivative of a constant, you'll always get 0. Next, if you get the antiderivative of 1 with respect to x, which we can simply write by the integral dx, you'll get x plus c. This follows from the fact that if you get the derivative of x with respect to x, you'll get 1. Next, if you have a non-zero constant, which you denote by a, if you get the antiderivative of the product of a with a function of x with respect to x, you can essentially factor out the non-zero constant a outside of the integral. Next, if you have two functions defined by f and g that are defined in the same interval, then the antiderivative of the sum of f and g is equal to the sum of the antiderivative of f with respect to x and the antiderivative of g with respect to x. And then you can make the same analogy when it concerns the difference between the two functions. Next, we have the power rule of antidifferentiation. So if you have a real number n that's not equal to 1, the antiderivative of x raised to n with respect to x is equal to x raised to n plus 1 all over n plus 1 plus c, plus constant c. So this follows from the fact that if you get the derivative of x raised to n plus 1 over n plus 1, you'll get x raised to n again. Now we have the concept of particular derivatives. So you wish to find a particular derivative capital f of x when you want your antiderivative to satisfy a given condition. Most of the time we call this condition the initial or boundary condition. Next, we have U substitution. So we use U substitution when you want to look for the antiderivative of very complicated functions. So you can have, most particularly when you're dealing with composition of functions. So a function within a function with a function can go on, so on and so forth. So if you have U be denoted, if you let the function g that's differentiable on a range in an interval I, and f is continuous on that interval I, and you let g of x be denoted by u, then you have the antiderivative of the product of f of g of x, the composition of f and g of x, multiplied to the derivative of g of x with respect to x. You can essentially substitute, since you have u equals g of x, you can substitute the g of x here with u. And then if you get the derivative of u with respect to its self, you'll get du, of course. And then if you get the derivative of g of x with respect to x, you'll get g prime of x dx. That's why this du will replace the g prime of x dx. Unfortunately, there isn't a clear and decisive method in terms of U substitution. Sometimes it's trial and error. Most of the time, you can try to look for what's the innermost function, or a function that's used frequently, or a function that if you get the derivative of, you'll be able to get the other terms that are in the expression that you'll be able to quote-unquote cancel out. So as practice for particular derivatives and U substitution, we have these three problems. Let's do them one by one. So in this first item, you want to look for the particular antiderivative of this quite complicated function whose graph passes through the point 0, 1. So of course, we first have to find the antiderivative of this function, an antiderivative, not a specific one yet, just the general form. So if you see here, what can be our possible candidate for u, you can see here that the sine x here is used 2 times. It's quite often, and then it's almost an inner function within the function, since it's the power of 2 here and e, the Euler number. So maybe let's try to use that as our u. So if you do, we know that if you get the derivative of u, you get du. And then if you want to get the differential of sine x, you get cosine x dx. And then if you do some manipulation here, you'll get dx equals secant x du. And as you can see here, that's going to mean something to us once we do our substitution. So if you do your substitution, you see here that the sine x has been replaced by u, and then your dx has been replaced by secant x du. Of course, you have a secant x here in the denominator. You can cancel out and then be left with this. And then in order to simplify more the complicated fraction we have here, you can divide 1. You can separate the 1 and the 2u, and you'll get this. And then knowing our subtraction theorem for antiderivatives, you can separate them into 2 separate antiderivatives, and then you can solve them one by one. For the first antiderivative, the e raised to negative u, you can substitute negative u with v, and then if you get the derivatives, you can get du equals negative dv, and then we'll apply the substitution to the first derivative. You get this. See, it's been substituted. We'll keep this as it is. And then you'll get this for the first antiderivative. Of course, this follows. So you'll take out the negative, since the negative here is essentially -1, and you can factor out the -1. And then, of course, the antiderivative of e raised to v with respect to v will stay as e raised to v. And then for this antiderivative, 2 over e is a constant, and then your u here's the indeterminate, and we're antideriving with respect to u. So this is a well-known theorem in antidifferentiation. So you'll get 2 over e raised to u all over 2 over e. Take note again that 2 over e is a constant. And then we get this, so we get this following expression. Don't forget always to put the constant c, since when you're antideriving, you're only getting the general form. We haven't yet applied the particular condition. And then we can apply our substitution. So of course, in our first substitution, we use v equals negative u, so you can replace the v with the negative u. And then we substituted u for sine x, so you can then replace the u with the sine x. And then this ln 2 over e here, the natural logarithm of 2 over e, applying the rules of natural logarithms, this becomes the difference between ln 2 and ln e. And then you can separate the 2 and e here in this power. So you put the e over raised to sine x here. And then we know that ln e is equal to 1. So yeah. So we have the general form here. This is our the general form of the antiderivative of our small f of x. Now we can apply our initial condition. So since we wanted to pass to 0, 1, that's essentially f of 0 is equal to 1. So we need to find a c that will satisfy this condition. So in doing so, we'll evaluate the x's at 0, and then you do manipulation. Of course, we want this to be equal to 1. We'll get this. And then if you move both of these constants to the right side, you get that c is equal to 2 plus 1 over quantity, the natural logarithm of 2 minus 1. Thus, this is our particular antiderivative for small f of x. Next, let's move on to this next problem. So we want to evaluate this antiderivative. So if you see here, this natural logarithm of sinh x is used 2 times. So it's the most frequently used function within the function. And then it's also innermost function within the expression. So let's try to use that as our u. It follows that we'll get du is equal to 1 over sinh x times cos x dx. This follows from a chain rule. And then if you see that you get cos x over sinh x dx, and we know that cos x over sinh x is equal to cot x, which is great for us because we have the cot x here. Or you'll have dx is equal to 1 over cot x du. So if we apply our substitutions, the natural logarithm of sinh x will be replaced with u, and then our dx will be replaced with 1 over cos x multiplied to du. You'll get this, since the cos x will be canceled out. And then you can separate this fraction into 2 separate terms. You get this. And then this is pretty straightforward. You'll apply a power rule for both of them, as you did here. So you'll have -3 plus 1, you'll get -2. And then it's the same for the denominator here. And then here you have -2 plus 1, you'll get -1, same here. Yeah. So you get this. This is the form here, if you continue. Again, don't forget your constant c, your indeterminate constant c, and then we go back to our substitution. We made our u equal the natural logarithm of sinh x, thus we replace it again. Yeah, that's our final answer. Finally, this is our final problem. Again, we need to find the antiderivative of this function. This looks very complicated, but if you look at it, you have the cosine x here. You have your cosine x here. It's used 2 times. It's the most frequent, and it's really the innermost function within this expression, because it's inside another trigonometric function. Here it's inside another trigonometric function, and it's a power. So let's use cosine x as our u. Of course, it follows that our u, the du, will equal the derivative of cosine x, which is of course sine x, which will be multiplied to dx. If we do manipulation, you'll see here that your dx will be equal to cosecant x du. So if you substitute again, you see here that your cosine x has been replaced with u, your cosine x has been replaced with u, and then you have here that your dx was replaced with cosecant x du, and then you have your cosecant x here in the denominator. That will cancel out. You'll be left with this. This is still a pretty complicated expression, so maybe we should apply u substitution again. You see here that your sine of u is the innermost function, because it's the power of this 2 here. So maybe we can use that as our next substitution. So let v equal sine u. If you get the derivative, you get dv is equal to the derivative sine u, which is of course cosine u du. Or you'll get du is equal to secant u dv. Be careful when you're using your letters, the uv. Be careful about that. It can get confusing. So see here, if you apply our given substitutions, your v has replaced sine u, and then you have your secant u dv. Thankfully, we have a secant u here in the denominator that will cancel out. We'll be left with this. And then we'll apply again that since 2 is a constant, and then you're anti-deriving with respect to v, and your v here is the power, you'll get 2 raised to v over lv. This is a follows from a formula that we have, remember that. And then, of course, once you're done having these integral signs, don't forget to already apply your constant, because you're only getting the general form. You're not getting a particular antiderivative. And then we'll apply again our several substitutions. So see here, we have our v's. We made our v's equal sine u. And then we made our u's equal cosine x. So we'll replace that again. Thus, we have this final answer. So again, there's really no particular way in doing U substitution. Sometimes it's just trial and error, but try to analyze first what you have in your expression. See maybe the simplest terms, what's a term that's used most often, what's a term that's the innermost function within an expression. It's really trial and error, so you just have to be careful. And then be careful when you're using your U's and V's when you're using several substitutions in a problem. Okay, I think that's it. Thanks, guys, for listening.